Hi, this is Math 1650, and this video is over section 8.3. We'll be looking at testing claims about a population mean using hypothesis testing. We're going to look at it with what happens when we don't know the population standard deviation and when we do know the population standard deviation. And then we'll end this chapter doing some more hypothesis testing involving both proportions and means where we know the population standard deviation. All right, so some assumptions here. First assumption is this is a simple random sample. And so this is something that will be taken care of in our data collection. So we know population, or actually that we don't know the population standard deviation. We'll start with that. And then we have a normal population for n greater than 30. It's important to know if we know the population standard deviation or not. Not wanting to save. It's important because if we do not know the population standard deviation, sigma, then more variability is added to the test. Right. So we use a t-test with a student t. Okay, so our test statistic is actually a t-statistic, not a z-statistic. And it's the mean for the sample minus the population mean over the, or the claim mean for that matter, over the standard deviation for the sample divided by the square root of n. All right, we will be using hypothesis testing on StatDisk. We have to go to analysis, hypothesis test, and select means. And then we may use summary statistics, or we may just use the data, which allow us to not have to input so many numbers, but we would have to import all the data for that matter. We're going to record the p-value, test statistic, and critical values, and then view the critical region. Right, so we're just going to start doing some examples here. So first, the body temperature. Test the claim that for a population of adults, the mean body temperature is less than 98.6 degrees Fahrenheit. Since the population standard deviation is unknown, it will be estimated using the sample standard deviation of 0.535 based on 12 observations with a sample mean of 98.39 degrees Fahrenheit. We'll test this at a significant level of 0.05. Alright, so step 1. Is we need to check requirements. We don't know the population standard deviation. We only have the sample standard deviation. So sigma is unknown. And we're going to assume a normal population. Alright, so we're testing the claim that the mean is less than 98.6 degrees. And this is again the claim. The opposite of this claim is that it's greater than or equal to 98.6. And so we set up our null hypothesis that the mean is equal to 98.6, and the alternate, which is the claim, is that the mean is less than 98.6. Okay, so this is a one-tailed test. And we're looking for a critical value that's going to separate the lower part, which is our rejection region, from the upper part. So we're looking to find that our sample mean is too low for it to be still 98.6. Our significant level is 0.05. And we are looking at a t distribution. With sample standard deviation of 0.535, n is equal to 12, and the sample mean is equal to 98.39. Alright, so we want to find the test statistic as well as everything else. So we'll go to analysis, hypothesis testing, mean, one sample. And we don't have the data, so we'll just put everything in. Right, so our alternate hypothesis is less than. Significant level is 0.05. Claim mean is 98.39. We don't know the population standard deviation. The sample mean, or sample size, is 12. Sample mean is 98.39. And the sample standard deviation is 0.535. And we evaluate. Sorry, my mouse is acting up here. We get a test statistic that is equal to roughly 0. You know what? I know why. Claim mean, that value was not 98.39, that's the sample, 98.6. I didn't think that was going to be the case. Alright, the claim mean is that it's 98.6. Right. Now hit evaluate. Okay, test statistic of negative 1.36. Critical t is a negative 1.795, so 1.8. P-value is 0.10. And let's look at the plot. And we can see this test statistic is inside our non-rejection region. Okay. So based on the critical region and the fact that the test statistic is inside the non-rejection region, and the fact that the p-value 0.1 is greater than 0.05, we will fail to reject the null. Right. So we can say that basically the sample's sample temperature wasn't low enough to say that it was different than the 98.6. So we can say we do not have evidence to support the claim that the body temperature is less than 98.6 degrees. So now let's do one, and well, let's look at when we do know the standard deviation. So here assumptions are very similar. Simple random sample, a normal distribution or n greater than 30, and the population standard deviation is known. Okay, this takes us back to a z-score, and so we'll see when this unstat this, you'll end up with a z-score. The procedure is just the same as what we've done, except we have a population standard deviation. But here we're going to do one where we have data though. Actually, I think we're going to do it without the population standard deviation, then we're going to add in the population standard deviation. So we'll add in the data first. So get that in there. So 0.38, 0.55, 1.54, 1.55, 0.5, 0.6, 0.92, 0.96, 1, 0.86, and 1.46. Just want to make sure I got 11, 3, 4, 6, 7, 9, 10, 11. Okay. I have missed one before, so I'm just double checking. Alright, go back to the Zoom. Alright, so here we have listed below are the measured radiation emissions corresponding to a sample of cell phones. We're going to do this on a 0.05 level of significance and test the claim that cell phones have a mean radiation that is less than 1.00 W per kilogram. So requirements, we don't know the standard deviation right now, so that is one thing to keep in mind. We're going to assume normal. Right, so first step is to write up the claim. Claim is that the mean is less than 1, and opposite of this claim is that the mean is greater than or equal to 1. And so our null hypothesis is that the mean equals 1. The alternate hypothesis is that the mean is less than 1, which is the claim. And so again, it's a one-tailed test, and we're looking at the lower region being the rejection region. Right. And we are looking at a significant level of 0.05, and this is going to be a t-distribution right now. Right. And again, we have the data, so let's find the test statistic now. So we'll go to analysis, hypothesis testing, mean one sample, use data. So we'll select the column 1. Significant level is 0.05, so that stays the same. Claim mean is 1, and we're doing an alternate hypothesis that is less than the claim mean. Alright, so we evaluate, and we get test statistic that is equal to negative 0.485, and we get a critical t of negative 1.81, and we get a p-value that's equal to 0.32. Okay, so based on this, we will fail to reject the null. Right, our p-value of 0.2 is greater than 0.05, that's why we're rejecting the null, and our test statistic falls well inside the rejection region. Okay. So we can say that if but we do not have evidence. We do not have evidence to support the claim that cell phone have radiation levels less than 1 W per kg. Okay, so now we're going to look at this and see what happens if we repeat this with a standard deviation for the population at 0.48. See what it changes. Okay, so what does change that we know? Okay, the claim and the hypothesis test, they're not going to change. Significant level is not going to change. The step 5 will have a z distribution. This is also then going to change step 6, which is going to be a z-score. Right, so let's go and perform this. So we're going to add in, what was it, 0.48 and run the evaluation. So now our z-score is equal to negative 0.427. Our critical z is now negative 1.645, and our p-value is now 0.33. So a couple of things have changed. Everything that has changed is in red. What hasn't changed is the results. Our p-value actually got higher, so it's definitely going to be a fail to reject, no. And our critical region, notice the critical value also changed. Now I will say the test statistic did get, I think, closer to that critical value, but not much closer. Right, so we still fail to reject the null, and so we still do not have enough evidence. In this case, the result was the same. All right, let's look at another one. Pharmaceutical company is testing a new pain relief drug to determine if it changes the average recovery time for patients. The company claims that the average recovery time without the drug is 10 days. The new drug is given to a random sample of 30 patients, and the recovery times are recorded. The sample shows an average recovery time of 9.2 days with a sample standard deviation of 2.1. Does the new drug significantly change the average recovery time? Alright, so here, again, we don't know population standard deviation. The claim is that the mean is equal to 10 days. So the opposite of the claim is that the mean is not equal to 10 days. So our null hypothesis is mean equals 10. And the alternate is that the mean does not equal 10. Okay, so we're looking at a two-tailed test. So we have two critical values. Alright, we are looking at a significant level, we'll say is going to be 0.01. It's not given, but we're dealing with health, so we'll make it small. And we're going to have a t-distribution. And so let's run the data, or run the test, I should say. Significant level is 0.01. This is going to be not equal to. Claim mean is 10. We gotta use some of the statistics. We don't have the data, so we put this in. Population not equal to 0.1 is your significant level. Claim mean is 10. Sample size is 30 patients. Sample mean is 9.2. And sample standard deviation is 2.1. Evaluate. We get a test statistic. That's equal to -2.09. Critical values are plus and minus 2.76. And p-value 0.045. Waiting for it to save. Let me go back to what I have. 0.045. So we can say that the test statistic falls inside the non-rejection region, and that the p-value, even though it's pretty low, do it this way, 0.045 is still greater than 0.01. So we failed to reject null. That did not look like reject. Reject null. We can say we have evidence to support the claim that the recovery time is 10 days. Okay. All right. If we were to change the significant level to 0.05, we would actually be able to reject this, but because our p-value then will be lower. So depending on the significant level would determine the results for this. We also want to look at different, let's say we have the population standard deviation be equal to 0.1 days. Let's see what happens with this now. Now we'll get a test statistic that's negative 43.8. And we'll get a z distribution. And we get p-value that is 0. So when we look at our critical value region, we're significantly lower in our rejection region. All right, and with the p-value, it's definitely going to be lower than any. When you get a p-value that's 0 and statistics like that, you know you got a rejection there because it's just that low. It may not be exactly 0, but it's enough on statistics that it's going to show all zeros, and that will change. So that would change our results. So in this case, we would reject the null and say we do not have evidence to support the claim. So the standard deviation, knowing the population standard deviation, it's very important. Notice we did not have, we did have the sample standard deviation. That did not matter as soon as we had a population standard deviation. Let me see. Oops, my tablet's going to die soon eventually. Let me see what time we have. Okay, I'll do one more. A company wants to test whether a new employee training program increases productivity. Historically, the average productivity score of employees has been 75 with a population standard deviation of 10. After implementing the training program, a sample of 50 employees show an average productivity score of 78. Has the new training program significantly increased employee productivity, or are we just looking at a sample fluctuation here? Okay, here we actually do know the population standard deviation is equal to 10, and we'll assume it's a normal distribution of the population. Our claim is that the mean score has increased and is greater than 75. The alternate, the opposite of this, is that the mean score is either less than or equal to 75. And so our null hypothesis is that mean score is equal to 75, and then the alternate is greater than 75. So this is a one-tailed test. With the left tail, or the upper tail, being the rejection region. Right, so we want to know if 78 is high enough or far enough above 75 to be a to show that it has helped employees. Right, significant level here we will use 0.05. And we are going to look at this as a normal distribution because we do have the population standard deviation. And so we're looking at a z-score here. And so let's throw in the values. Right, first, the alternate hypothesis is that it is greater than the claim mean. Significant level 0.05. Claim mean 75. The population standard deviation is 10. Sample size is 50. Sample mean is 78. And we don't have the sample standard deviation, but we have to enter something. So we just enter the population standard deviation. You can actually enter anything, and it won't make a difference. I don't know why this is one particular time it does not allow you to just leave it blank. Well, I'll show you here real quick that I could put anything here and it's not going to change anything. So I get my test statistic. So let me show you. If I enter 5, it doesn't change. Enter 500, it doesn't change. So you can just enter a number. Okay, test statistic is 2.12. Critical Z is 1.645. P-value is equal to 0.017. Alright, so let's look at the plot. We are clearly in, the red is the critical value, we are clearly in the rejection region. So what this means is we reject the null hypothesis. Okay, we have evidence that 78 is high enough to say that it is no longer an average of 75, and the training program has helped some. So we have evidence to support that the new training program has increased productivity. Okay. Alright, so I'm going to stop the video here. The last video in chapter 8 is going to be on just a few more problems that you can practice beforehand, and then go in and see how well you've done and fix what you need to fix. They're all going to be on sample examples of hypothesis testing, both proportions, mean, and means with known population standard deviation. Alright, I'll see you then. Bye.